that the function f mapping R to R defined by fx equal to sin x for all x belonging to R is neither 1, 1 nor on 2. So this is kind of like a reverse form of the previous sum that we did. Now, again we go by the same approach. So let's assume two numbers alpha and beta in the real set of numbers. So we assume two same children. We assume fa equal to fb. We consider the same child. If a equal to b, then under this assumption and by the function that we had considered fx equal to sin x, f a alpha can be written as sin alpha and f beta can be written as sin beta. So f alpha equal to f beta implies that sin alpha equal to sin beta. Now, if sin alpha equal to sin beta, then alpha is actually equal to n pi plus minus 1 whole to the power beta. Sin alpha equal to sin beta does not imply that alpha equal to beta. Sin alpha equal to sin beta, there may be a situation where alpha is not equal to beta, but sin alpha is equal to sin beta. For example, you can consider the situation where sin 0 degree is equal to sin 180 degree, which both of them are equal to 0. But obviously 0 is not equal to 180 degree. So sin alpha equal to sin beta does not necessarily imply that alpha equal to beta. There may be a situation that alpha is not equal to beta, but sin alpha equal to sin beta. So when we are considering the same child, sin alpha equal to sin beta, that does not necessarily mean that the parent is the same. Here, since we have to prove that it is neither 1, 1, we essentially prove that it is not 1, 1. So it's actually many 1, as I have mentioned here. So we are considering the mother and the father, and we are mapping both the mother and the father to the same child alpha equal to sin beta. So we have alpha, we have beta, and we are mapping both of them to the same value sin alpha equal to sin beta. So f is not 1, 1. In fact, f is many 1. So we have proved the first part. We have proved that it is not 1, 1. Next, what we need to prove that it is not on 2. So let's say minus 1 less than, not let's say, we know that minus 1 less than equal to sin x less than equal to 1. So the value of sin x can vary only between minus 1 to 1. It cannot be minus 2, minus 3 or 2, 3. So for x belonging, x is the angle of the angle value here. So x can belong to any number. X can be 1 degree, 2 degree, 3 degree, 4 degree. It can be any real number, which is the domain set. But the range set, as they had mentioned before, this function maps R to R. So in the range, in the domain set, they are considering the set of real numbers, and in the codomain set, they are considering the set of real numbers. What we essentially need to prove to say that it is not onto is that the codomain set and the range set is not the same. So when we map any value in the real set to its image, we get a range set, and that range set is a subset of this real codomain set. So that is essentially what we'll be doing. So we have this domain set x belonging to R, but for any value of x belonging to R, the value of sin x will lie between minus 1 to 1, which is essentially a subset of the real codomain set. So you see, range of f is not equal to codomain. Range of f is a subset of codomain. So f is not onto, in fact f is an into function. So going by the previous previous statement, we had said f is not 1, 1, f is many 1, and f is not onto, f is into. Hence we can say that f is neither 1, 1 nor onto. The next sum that we'll be doing is, let A be a set where A consists of the three elements A, small b, and small c. Write all 1, 1 functions from A to A. So the function f, let's say, maps A to the same set A. We have one non-empty set A, and the function f maps elements of A to elements of B. So the first thing that we consider when we do this is Since f maps A to A, that means when we map an element, we come back to this set itself. So f of A will either be A, B, or C. It will remain in this set. So that's one condition that we need to remember. Next, what we need to remember is the functions need to be 1, 1. So let's define 1, 1 functions once again. I have defined them in my part 1 of these set of videos based on mappings and functions. I will do it again today. So a mapping or a function if mapping A to A is said to be 1, 1 or injective mapping or injection if different elements of A have different images in A. So if A is a if A is the domain set and A is itself also the codomain set, then we cannot have two elements which are mapped to the same element. So if you remember, I had taken the example of mother to children. I cannot have two mothers who have the same children. So every element in A, the domain set, will have different elements in the codomain set. So the first thing that we do is, the easiest way to answer is, I first write FA, FB, FC, FA equal to A, FB equal to B, FC equal to C. That's the easiest one. Next, what I do is I again write FA, FB, and FC, and I need to find another combination ABC which is not in the same order, but they do map in ABC back to itself. So what I do is I write A. So in this second portion, I have FA mapping A to A, FB maps to C, and FC maps to B. So here, as you can see again, every element has a pre-image. So A has a pre-image in A, B has a pre-image in C, C has a pre-image in B. They are all single elements which are being mapped from each other without any repetitions, and they are all unique in nature. So the condition of 1, 1 is again satisfied. The second mapping is if A maps to, if A is B, if B is A, if C is C. So here again you can see the condition of 1, 1. So the uniqueness property again holds. And we move on that way. So the easiest way to write them down in the examination hall without missing out on any of the mappings is, first you keep hold of A and you write BC and CB. So you keep hold of the first one and you change the last two. In the second step, you keep hold of the first one again, but skip this, go to the next value of A, go to the next value of the first function, and then you skip. So what you essentially do is you keep A, then you write BC, CB. Then after A, you have B. What are the two other letters you have? You have AC, CA. Then after A, B, and C comes C. What are the other two letters you have? You have AB and BA. So in this way, if you write down all the functions, then you will not have been confused as to which function you have written or not written. The only condition that you need to remember is they need to be 1, 1. So you cannot have if A equal to A, if B equal to A, if C equal to A. You can only have 3 in each line. So you can only have if you use up A in one of these right hand sides of the equation, equality sign, you cannot use them again in the equality in the right hand side of any other equality sign. So that is one way that you can approach this sum. These sums are usually more common in MCQ type questions. So they sometimes say, how many 1, 1 functions will you find? So you can write them down in the rough work section and you can see that 6 such mappings. So there are 6 1, 1 mappings from A to B, A to A itself, and they are given by 1, 2, 3, 4, 5, and 6 mappings. So this is another sum that we cover. The next sum that we see is, let A be the set of triangles in a plane and R plus, so it's the positive set of real numbers, R plus be the set of positive real numbers. Then show that the function A mapped to R plus defined by if x equal to area of triangle x is many one and onto. So here fx is not exactly a mathematical function, this is a conceptual function. This is, if I consider an area, then fx will be the area of that triangle. So let's say I consider this triangle. Fx, that rule will tell me what is the area of that triangle. So that is how my function works in this sum. So we need to show that this fx function is many one and onto. Now let the first thing that we'll concentrate is the many one aspect of the function. So when we consider many one function, we essentially, if we consider the example, then the mother children example does not work. So we essentially have two parents and one children. So we have two elements which can have the same result essentially. So we can have two triangles and we can have the same result of the fx. So that's what we'll do. We'll first prove that this function is many one. So assume two triangles, triangle 1 and triangle 2, and assume that they have same area. Remember, we are not considering the same triangle. We are considering the same function of the triangle, which is the same area of the triangle. So that is the section where people sometimes get confused. We are starting from fx. If this is the triangle portion, then this is the f portion, which is the area portion. So we start from this side. We start from the result side. We start from the area portion of the calculation. So we assume that for two triangles, triangle 1 and triangle 2, the area of those two triangles is the same. So f of triangle 1 is equal to f of triangle 2. That means area of triangle 1 is equal to area of triangle 2. But area of two triangle being same does not necessarily mean that f1 and triangle 1 and triangle 2 are the same triangles. You might know from the explanation that if this is one triangle, if there are two triangles which have the same base and the same height, then they are said to be then they have the same area magnitude wise. So let's say this is a parallelogram, then the area of this triangle, let me mark it this way, and the area of this triangle, they'll both be the same. So these two triangles are not the same. This triangle is one triangle, this is another triangle, but they have the same area. So area of two triangles is same does not necessarily mean that both the triangles are the same triangle. So you see two triangles, two different triangles are being mapped to the same magnitude of area. So this is a many one mapping. As I have written, if triangle 1 equal to f triangle 2 does not imply that triangle 1 is identical to triangle 2. So f is a many one mapping. The next part that we need to prove is, as the Sam had mentioned, onto. So now we need to prove that this function is onto. Now for onto mapping, we need to show that codomain set is equal to the range set. So we have the domain set here, which is the function, which is the set of all triangles, and we have the domain set here, which is the set of all areas, or set of all real numbers rather. So we need to show that for every real number in this set, there exists a triangle whose area is equal to this number. So if we have 5, 6 and all the set of real numbers, there will always exist a triangle whose area will be equal to that real number. So let y equal to let y belong to the set of real numbers. So let us consider some real value y in the codomain set. Now, as I mentioned before, there always exists a triangle such that the area of the triangle will be equal to y. So there will always remain one triangle whose area will be equal to y. So if y equal to 5, we will always have at least one triangle whose area is 5 square units. So that is what I've written. Function of that triangle will be y, which essentially means that the area of the triangle will be y. So there will not exist any number who does not have a pre-image in the domain set. So by definition, f is onto. Now in condition 1, we had explained that f is many one, and in condition 2, we are explaining that f is onto. So combining both of them, we can say that f is many one and onto.